Hello everybody and welcome to day 4 of the 12 projects of Codemas. This is a series that I'm doing on the Pihut Maker Advent Calendar. My name is Astronaut. I'm a Linux Systems Administrator and yeah, let's get right on into it. Alrighty, day number 4 unboxing. Let's see what we got. Looks like we have one 10K, and I'm probably going to butcher this, but potentiometer. One potentiometer knob, one washer, which may be fitted to the potentiometer already, one nut, and 3 more jumper wires. Alright. Alright, let's get started. Maker Advent Calendar Day number 4, Amazing Analog. Welcome to Day 4 of your 12 Projects of Codemas Advent Calendar. Today we'll be playing with analog inputs using a potentiometer and combining this with some components that we've already played with. Our code so far has been on, off, or high-low using digital inputs and outputs. With today's component, we're going to explore analog inputs, which will work in a different way. Tip, you'll find that some people in the maker world use analog and others prefer analog. It's all the same thing. Box 4 contents, as we saw, we had one 10K potentiometer, one potentiometer knob, one washer, nut, and 3 motor-mill jumper wires. Today's project. Today we're exploring the wonderful world of analog. Until now we've been using digital signals with the buttons and LEDs in our calendar. Digital signals are strictly a 1 or a 0, high or low, on or off. It's one or the other and nothing in between. Analog signals offer a wide range of numbers to represent values instead, which is much more suitable for sensors, dials, and similar components. Think of digital as a light switch is either on or off. Think of analog as a volume dial on a stereo. You can twist the dial to gradually turn the volume up and down by small amounts. Our potentiometer can pass these analog signals in the form of voltage to our Raspberry Pi Pico, giving us a gradual input with a wide range of values for us to play with in our code. Alright. What is a potentiometer? A potentiometer is a variable resistor. Our calendar already included traditional resistors for the LEDs, but these were at a fixed value offering a specific amount of resistance. A potentiometer is a resistor that can have its value changed by turning the knob. The potentiometer in your box is a 10K potentiometer, meaning it can be set anywhere from 0 ohms to 10,000 ohms. Resistance is measured in ohms. The way we're going to wire our potentiometer allows us to use it to send a varying voltage value to our Raspberry Pi Pico with some special pins, which some special pins can read, convert, and provide a value we can use in our projects. We're going to explain those pins in a few moments, but for now let's get the circuit built. Alright, make sure your Pico's USB cable is unplugged. Grab your potentiometer, slide the flat washer over the dial, and then screw on the included nut. These may already be fitted. Then with the potentiometer legs facing downwards, turn the dial all the way to the left and fit the knob with the colored line pointing bottom left like a radio that's turned all the way down. Leave the LEDs and ground wire in the blue lane in place from yesterday's box, but remove the buttons and all other parts. This is our starting point. Okay, so we're removing this stuff. Alright, let's see. Yep, alright, I think we're good there. Oh, it actually wants me to remove this stuff. grab your potentiometer. Alright, so slide the flat washer over the dial. And then screw on the included nut. I'm guessing that's what it's wanting me to do, so. With the legs facing downwards, turn that dial all the way to the left and fit the knob with the colored line pointing bottom left. Alright, I guess that's good. Grab the mini breadboard and fit the potentiometer to the front edge facing you. Okay, so should these be bent downwards? Alright. Let's see. Next we need to connect the potentiometer to our circuit. The right pin needs to connect to the 3v3 out pin, physical pin 36, the middle pin to GPIO 27, which is physical pin 32, and the left pin to ground. Use the blue lane as we already have that connected to ground for the LEDs. Alright. Alright, I think that's good. Activity 1, printing analog values. Let's start with a simple program that continually prints the analog reading from our potentiometer. We're specifically using GPIO 27 as this is one of the Pico's ADC pins. But what is an ADC? If we look at our Pico pin map again, we'll see that there are 3 dark green ADC pins available on the right. GPIO 26, 27, and 28, which are physical pins 31, 32, and 34. An ADC is an analog to digital converter. The ADC pins on our Pico have the special ability of being able to convert an analog input into a digital form we can use. We have to import ADC into our code to use this feature. Note, we'll also spot ADC_VREF and AGND pins, but we're not going to go into those pins in this calendar as we don't strictly need to use those for our example. We'd rather not overcomplicate things while we're still learning the code. Let me pull up. The code below imports ADC and sets GPIO 27 as an ADC pin. Then we start a while loop which prints the potentiometer's value every second. The read_U16 part does this, taking the varying voltage applied to the pin from our potentiometer and scaling this to range of usable output values between 0 and 65535. For those who want to get technical, the Pico's ADC pins are 12-bit, however MicroPython scales this to a 16-bit range, which is 0 to 65535. Run the code below and then try turning the dial. Watch the values go up and down as you turn the knob from right to left. The values don't always go right down to 0, this is normal. This is where everything above should start to make sense. Alright. So 208 right now, and if we turn this, all right, so we see the numbers super high and then going down. All right, sweet. Activity 2, control LED flashes with analog values. So what can we do with this large range of input readings? One thing we can do is use it in our code to control other components, such as our LEDs. Whereas previously we have turned the LEDs on or off with buttons, the wide range of output readings allows us to tell our code to do different things depending on whereabouts it is in the range. The code below uses the readings to control how fast your LEDs flash. We do this by making a time delay variable. Variables for time delay. We used a variable to make a counter in day 2, which we constantly updated. This time we're using a variable to allow us to set a value in one place rather than having to search through our code for all the various time delays. For example, let's say that we have 5 LEDs in our code and we use a time delay of 1 second after every flash. From what we've learned so far, we could use time.sleep1 after every flash. This works fine, but it's a bit of a pain to update all those lines every time we want to adjust the flash speed. Instead, we can create a variable and assign it a name such as myDelay and give it a value, say 1. We can then change our time delay lines to refer to this variable instead of entering a number directly using time.sleep myDelay instead. Now, to update the speed of each flash across our entire program, we only have to update the myDelay variable. While we only use the delay once in the example below, we thought it was still a nice opportunity to show you another way of using variables to save you time and improve your code. All right, the code. The example code below takes a reading from the potentiometer, divides the reading to give us a number that's more usable as time delay, assigns the divided reading to the variable myDelay, uses that delay variable to control how long the LEDs are left on and off to create a flashing sequence. Turn your knob to around halfway to start with, run the code below, and then try adding in other LEDs and making them flash as well, or try adding a print line to the end of each of the while loop to see what the value myDelay is using. So let's put it in the middle, copy this over. And as we crank this up, we can see it's blinking a lot slower. And turning it all the way down. All right. So I guess we get to a point where it's so low it just always stays on. Alright, so let's see. Geometer ADC pin 27. Alright, so here we go. Let's just still this. Try adding a print line at the end of each while loop. Alright, I broke something. Alright, I broke the actual physical circuit, not something, a typo or something, I guess. So hopefully you can see that pretty good. All right, so we see my delay is about 0.26, and I turn it down, and it goes crazy low. And then it can go all the way up to 1 second. All right, I think we should be good there. Activity 3. Light LEDs depending on the potentiometer value. We can also use the wide range of analog values to trigger an action depending on whereabouts in the overall range we are. We can do this by using if statements again, this time with conditions that look to see if the value is higher, lower, or between a set range. In our example below, we use a few if statements to check if the reading is less than 20,000, between 20,000 and 40,000, or greater than 40,000. To make our if statement look for less than or equal to, we use a less than or equal to operator, like this, if reading less than or equal to 20,000. To make our if statement look for a value between two numbers, we use a slightly less obvious combination of two less than operators, like this, if 20,000 is less than reading is less than 40,000. To make our if statement look for greater than or equal to, we use a greater than or equal to operator, like this, if reading is greater than or equal to 40,000. Give it a spin by copying the code over to Thani, running it in your Pico, and moving the dial left to right slowly. Remember, the code commentary is there to help you understand each line. All right, so we see the amber is lit up at 32,000. At 15,000, or yeah, 15,000, we see the red gets lit up. And then if we crank it all the way to the right, we see the green lights up, since that is above 46,000. All right. So we set up the potentiometer, set up the LED pins, create a variable for our reading, run forever, read the potentiometer value, and set this as our reading variable. Reading variable value. Print the reading, short delay. All right. So if it's less than 20,000, the red was on, as we saw. If it's between 20 and 40,000, then the amber is on. And if it's greater than 40,000, then green is on. Activity 4, LED fader using PWM. Now for something a little more advanced but really cool. We're going to fade an LED in and out using our potentiometer. To do this, we use PWM. What is PWM? PWM stands for pulse width modulation. It's a type of digital signal where we, over a set period of time, decide how long the signal is on or high and how long it's off or low. This very fast on-off signal can create a fading effect for LEDs and can also be used to control robotic components such as servos. I guess that's how you say that. Our code needs some values from us to enable it to run PWM for us. Duty cycle and frequency. What is PWM duty cycle? We can decide how long we keep our LEDs on or high by changing the duty cycle. The duty cycle is the percentage of the time that our LED will be on. The higher the duty cycle, the longer the LED will be on, and the brighter our LED will appear. Duty cycle for the Pico in MicroPython can range from 0 to 65535, which is handy as this matches the output of our potentiometer. So we can use this value directly without having to manipulate it. What is PWM frequency? Our PWM code also needs a frequency value, which is the number of times per second that we will repeat the on-off cycle. We use 1000 in the example below. The code. So now that we know what PWM duty cycle and PWM frequency is, let's try it out. The code example below introduces a few new elements. Firstly, we need to import PWM. We set our light pin up a little differently to set it as the PWM output using LED equals PWM pin 18. We set the PWM frequency with PWM frequency 1000. We create a variable to store the potentiometer reading and start it at 0 using reading equals 0. The while loop then reads the potentiometer value and stores this in our reading variable and prints this for us to view in Thani. The LED is then given this reading as the duty cycle is using LED.duty_U16 reading. This is followed by a very short delay, then the loop continues. Copy the code over to Thani, run it, and then turn the dial left to right. All right, so we have some loose connections going on. Okay, so hopefully you can see that pretty easily. The red is super dim. Okay, so I guess we're just doing one single pin. So let's see if we change this to 1819 2019. All right, so amber is okay. Turning that down and up. And then green would be 20. Oops. All right, yeah, so there's all of them. Okay, so we see the readings getting printed there. I'm a Vim guy, so using all this mouse and clicking around here is painful. I'm sure there's a better way to be doing this that I just don't know yet. All right, let's see if this works for all of them now, unless I just destroyed this. Sweet. So you can see they're all turning down and up now. All right, day number 4 complete. Well done, makers. We know today was a little heavier as we introduced slightly more advanced topics such as analog and PWM. So take the time to go back over today's examples and play with the code if you'd like more practice. Make it, break it, fix it, learn. Today you have learned about analog and the difference between analog and digital signals, built a circuit with a potentiometer, learned how to use the ADC built into the Raspberry Pi Pico, controlled LEDs with an analog signal, and learned about PWM, including duty cycle and frequency. Keep your circuit safe somewhere until tomorrow. Don't take anything apart just yet. See you then. Thank you for watching and for stopping by, and tune in tomorrow for day 5.